Welcome everyone to the October edition of the GoldSim monthly webinar. My name is Nick Martin. I work with GoldSim Technology Group. And today's webinar, we're going to talk about Monte Carlo simulation, uncertainty, and probability. And this webinar is actually a rerun of one of the presentations at our GoldSim user conference in September. Before we go ahead and dive into the webinar, if you have any questions during the webinar, just use the raise your hand button or the chat text window and let me know you have the question, and I'll try to catch the question in a timely fashion and respond to you either in the middle or at the end, and we will have time for questions at the end. Okay, to go ahead and get started with the webinar, as I said, it's Monte Carlo simulation, uncertainty, and probability. And just as an overview of what we're going to talk about today, let me go back one there, sorry about that. It's an overview of what we're going to talk about today. In terms of an outline, we're going to start out and we're going to just sort of set the framework by talking about simulation in general, and then use that as a way to focus in on to probabilistic simulation, and then further focus into Monte Carlo simulation, and talk about some of the the options within GoldSim for conducting a Monte Carlo simulation. And at the end, we'll wrap up with some frequent questions we see at GoldSim Technology related to Monte Carlo simulation. Okay, so simulation, and especially in the way we think of it here at GoldSim, we think of simulation as a holistic process which involves creating a model, which is just a representation of a system, and using that model in an attempt to understand the factors which either control the system or in an attempt to predict the future behavior of the system. So simulation in and of itself doesn't really include any sort of value judgment in terms of the effectiveness of the simulation or the worth of the simulation. Simulation doesn't say anything about how well your model represents the system. It's just purely saying that you are making an attempt to represent the system. And also simulation, there isn't any sort of value judgment related to the ability of the model or sort of the utility of any forecasts or predictions made by the model. In terms of simulation types, there are many different types of simulation. One type of simulation would be physical scale modeling, where you could use a small version of reality to try to understand or predict what might happen in the future, in the larger version or in reality itself. But GoldSim is a computer program, so in GoldSim, all the simulations we're going to talk about, of course, are numeric simulations. And just as a way to sort of categorize the simulations and provide the background to move on to Monte Carlo simulation, there's sort of two types of, or two different categories we often use here at GoldSim to talk about simulation and just to categorize simulations of different types. These two categories are simulation time and model inputs. Okay, in terms of simulation time, as a way to categorize a simulation, in GoldSim, many times we're dealing with sort of two main categories, either static simulation or dynamic simulation. In static simulation, the system does not change with time, and you have one answer, or sort of a constant answer, from the simulation. In a dynamic simulation, the system changes and evolves with time in response to both external and internal influences. And then you have one answer for each point in time. So the other way to categorize simulation would be simulation inputs. And so with simulation inputs, we're talking about the model inputs then. The simulations could be deterministic or probabilistic, and again, this is purely referring to the model inputs. In a deterministic simulation, inputs are represented using a single, using a single value. It's kind of a constant value. The idea is it's a known. You know exactly what that value is, and that's the value that should be used in your calculation. Conceptually, that's kind of an immutable known, but in practice, you could see a best or worst case single value estimate, or use a best or worst case single value estimate in your model. All right. Then probabilistic inputs would be what you would use for probabilistic simulation, and this is in contrast to deterministic inputs. But for probabilistic inputs, you have inputs which do not have an exactly known value, and you represent those unknown values are not exactly known values with a probability distribution. And you can see on the screen at the left side there is the GoldSim stochastic element, which is the primary way to bring a probability distribution into GoldSim, or to let GoldSim know about a probability distribution. And on the right-hand side, you have just several plots of different normal distributions, which is a common theoretical distribution. And we'll talk about that a little bit more. All right, so I do have a note on the screen that somebody can't hear me anymore. And just to reconfirm that people can hear me, one or two people raise their hands again. All right, very good. Okay, so it looks like most people can hear. If you can't hear, I think it's something with your connection, and I would suggest trying to reconnect to the webinar. All right, continuing on then. So we're going to focus in a little bit more on probabilistic simulation now. So we've seen we can characterize simulations according to simulation time, deterministic, static or dynamic. And we can also characterize simulation in terms of simulation inputs. And now we're going to talk about probabilistic simulation, which is where we're looking at input uncertainty. Okay, so an uncertain input or parameter is described as a probability distribution to express our ignorance in the exact value for that input. Okay. And so things are uncertain when they aren't exactly known. And what we're often dealing with this is we're saying, oh, the value, our input value is constant in time. So it could be a fixed value. We just don't know exactly what that value should be for one reason or another. Or maybe we have a value we've chosen to use as a representative value, but we know it's representative and it was actually measured somewhere else or defined somewhere else. And we don't have any real sort of constraint on how well this might apply to our particular situation. Okay. So we talked about an uncertain input, and we could represent that with a probability distribution in probabilistic simulation. But there's another sort of uncertainty component that you can use probabilistic simulation to address, and that would be, so you could have actually a stochastic or random variable, which changes with time and can only be described statistically. So this would be another way. You're representing, in this case, you're really representing a physical process uncertainty. You have a stochastic variable, and you're representing a process that either we don't really understand or you can't really adequately describe given the current data or computational limitations. Okay, so a stochastic variable then represents process uncertainty. And so we have an uncertain variable, which we don't actually know the value of, and we have a stochastic variable, which represents uncertainty related to a physical process. Okay, so talking a little bit more about uncertainty. So what we've said so far is that uncertain and stochastic both denote uncertainty. Uncertain is the lack of knowledge related to an input value, and stochastic is uncertainty about how a physical process works or can be represented. For both of these cases, you could represent this input, whether it's a stochastic input or just an uncertain input, with a probability distribution. And in this case, the probability distribution provides an explicit representation of the degree of certainty surrounding the value, or sort of in contrast to that, the lack of certainty surrounding the input value. Okay. So with probabilistic simulation, we're, kind of the key here is that we'll be using a probability distribution to represent an input. And a probability distribution then just provides a compact representation of sort of a complete population or a complete set of values. So basically it provides the range of values that are possible and sort of the frequency or probability of occurrence of each value. So if it's a probability distribution that represents a population is a collection of all the values or individuals that are observed are possible. It could also be a probability distribution that represents a sample or subset of a population. So it wouldn't have all the values that are possible, in the underlying population. And kind of one way to distinguish that, if you have a probability distribution for an entire population, you would have, your probability distribution is kind of the truth. It describes everything about the entire population. Whereas if you have a sample, really you have a probability distribution that's based on that sample, but that's then, really just a guess at the probability distribution for the underlying population. And so, how good that guess is, purely dependent on how well the sample represents the underlying population. All right, so now we're going to actually look at a GoldSim model, and this is a very simple GoldSim model. And really, it's just providing a vehicle. It's really just providing a vehicle so that we can, talk a little bit more in depth about probability distributions and providing a way to sort of look at probability distributions in GoldSim. So this model is really, all it has is, you can see down here, let me page down for you, these three GoldSim elements with a bunch of explanation. And so really we're just using this model to present some definitions, and these definitions are, very helpful when you're thinking about just probability, using probability distributions and, representing probability distributions in your model. So frequency is the number of times a value appears in a sample or population. And then probability is the frequency purely expressed as a fraction of the sample size in this case. So, if the number of times a value appears in a sample is little n and there's big N values in the sample, then the probability is little n divided by big N. Okay? A distribution then is the summary of the values appearing in a sample and the frequency or probability of each value. The sample needs to be a collection of independent, randomly distributed values in order to, mathematically define it as a distribution. An empirical distribution is a distribution calculated from a finite sample or basically from a collection of observations. By definition, this kind of distribution isn't going to include all values in the population. It's just representing, the sample of observations. A continuous distribution is just a distribution that's described by a continuous function. An empirical distribution can be made or transformed into an empirical continuous distribution through the use of smoothing. And this is often this is usually what's done in GoldSim for the distribution result elements. And we'll look at those in a little more detail in a bit. And if you want some details about how GoldSim does that, there's a good knowledge base article shown in blue here in the center of the screen that goes through how GoldSim, will do the smoothing to represent that probability distribution that comes out in a result element. Okay, Smoothing could also be more complicated, like fitting a theoretical distribution to a sample. And that's a standard approach that's used in extreme event analysis. But a theoretical distribution then, that we could fit to a sample, is just a continuous probability distribution described by a closed form mathematical model or set of equations. And this model is actually just presenting one of those that's available in GoldSim, and that's the exponential distribution. You can see the definition of this distribution, the statistical moments of the distribution, and some typical plots. And then this model really just has a stochastic element, which is here, the theoretical distribution. And so this is kind of the main way to get a distribution into GoldSim, or to tell GoldSim about a probability distribution. And that's, it has this main part of the dialog here, and that's covering the mode, which is when the distribution is sampled, as well as the definition of the type, and you get to the type definition information using the edit button. And the edit button brings up the distribution, and in this case, it's a simple distribution to specify. You just need to specify the mean, and then the underlying closed form mathematical equation is used to generate the actual form. Okay? So you can see here the list of all the distributions that are available are predefined or are pre-coded into GoldSim that you can then use just by specifying the relevant parameters. The sampling is used with Monte Carlo simulations, and we'll see that as we go on. But sampled once just means it's this element of values picked from this element once each realization at the beginning of the realization. There are some advanced options here, which we're not going to talk about very much today, but these are all covered in detail if you use the help button or look in the GoldSim manual. So another sort of thing when we're talking about Monte Carlo simulation is the simulation settings here off the Run menu provide the main access to the global sort of GoldSim Monte Carlo simulation settings. So here you can see we're running 25 realizations. So we're going to run this model 25 times. The model's a static model, so all that's going to really happen in this model is we're just going to pick a value from the distribution and record it in this expression element, which we wouldn't even have to do, but then we're going to plot it using this distribution result. So no time elapse, it's just sampling from the distribution each realization to get 25 values, 25 randomly selected values. So if I run this simulation, we can then look at this result, and this is a distribution result element. So here you can see the theoretical distribution, which is just this exponential distribution compared to the distribution made from the sampled values, which is what this model is doing. So those would be just this value here. And if you look in the setup for this element, you can see we're actually plotting the distribution of the theoretical distribution. So we're just plotting the underlying exponential distribution there. And here we're plotting the empirical distribution, the smoothed empirical distribution, which we get by sampling that distribution. So to look a little bit more at probability distributions in GoldSim, I'm going to bring up one more model. Okay, I think that model's probably come up for everyone now. So this is actually a model from the GoldSim example models. If you're not familiar with the example models, if you go to File, Open Example, there are a number of models that are shipped with GoldSim. So if you have GoldSim installed, you have these models. This particular one is under the General Examples, and it's called Stochastic Distributions. Oops, let's see, so it's in here. Sorry, it's in Stochastic under General, and there's Stochastic Distributions. So that's where this model comes from. All it does is really just provide a listing of all these sort of predefined distributions in GoldSim. And so you can see these here. Most of these are theoretical distributions like the exponential, where you're just entering a parameter. And GoldSim has the closed form equations built in and will then, generate the full form of the distribution for you. But there are several types. The discrete distribution is one of them, where you as a user actually enter the distribution in terms of values and probabilities. The discrete, only has, it's not smooth between the values, so they're discrete values. But there are a number of more continuous distributions that you as a user can enter, and those would all fall under these user-defined distributions. So the common one would be this cumulative distribution here, and you can, enter your cumulative probabilities and your values to generate a distribution, or to tell GoldSim about a custom distribution. Okay, so we looked at those two models, and now we have back looking at the slide deck again. And so, in thinking about a distribution, one thing that often comes up is people randomly sample a time series, and that is, pretty much equivalent to sampling from a empirical distribution. It's a representation of the sample, or it's a sample representing an underlying population. And it would be, it's very equivalent to just using a discrete empirical distribution to represent the sample. You just haven't gone through the work of, collecting all the values and actually determining the frequency. You're just accounting for the frequency by having, all the values n times in the sample and randomly selecting from the sample. And the other model we looked at was that example model. And so the big thing from these two models is the stochastic element in GoldSim is a means to defining an input distribution. And if you look at the properties of the stochastic element, you can see how often it's sampled or how it's sampled. And we'll continue to look at a variety of examples of this as we continue to go through the webinar. The other thing the stochastic element provides, which we also looked at, is it provides the user a way to enter a sort of custom distribution. So this would be one way to enter a theoretical distribution, for example, that GoldSim doesn't provide prepackaged. An example of this might be the Pearson type 3 distribution, which is commonly used in hydrology. GoldSim doesn't have a closed form representation of that built into GoldSim, but there's no reason you couldn't generate the, sort of a CDF of that distribution in R or another statistics package, and then use one of the the continuous distribution definition in the stochastic element to bring that into GoldSim. All right, so let's get back to probabilistic simulation a little bit more. And so the big thing with probabilistic simulation is, what we're saying is, oh, we're doing this because we have uncertainty in the inputs or uncertainty in our process representation. The whole point here is we want to propagate that uncertainty surrounding our knowledge of the system or the model inputs. We want to propagate that uncertainty to the results. Okay, what does that uncertainty in input mean for the results from the model? And so that's uncertainty propagation. And you can see here the little schematic kind of walks you through that process. You start out with random inputs, and you randomly select a value from each of your random inputs, and then you run a deterministic simulation or computation on those values and aggregate the results. Okay. So uncertainty propagation is, the thing we're really looking at here, and that's what leads us to Monte Carlo simulation. So the idea here is that the result of any analysis or model that's based on inputs or uses inputs represented by probability distributions, where you have multiple realizations. So you have a range of different input values you look at with multiple simulations. So the results from that kind of simulation are always going to be a probability distribution, right? You're actually, because you have a range of input values, you're actually expecting to produce a range of output values. And you can represent that range of output values with a probability distribution. And so Monte Carlo simulation is a common modeling technique for propagating the uncertainty in a system to the model results. And so that is really what we're using Monte Carlo simulation for in GoldSim. And Monte Carlo simulation is the technique that GoldSim uses for uncertainty propagation. So in general then, Monte Carlo simulation is just a method of computing probabilities for results by simulating deterministic processes with randomly selected input values. So you have a range of different input values, you simulate those to the system deterministically based on that variation in inputs, and that gives you, hopefully, a variation in results. Okay, so where does the name Monte Carlo simulation come from? The name really comes from purely a reference to Monte Carlo in Monaco, which is famous for its casino, because generating these random numbers or random input values makes people think of casinos. So one of the things in terms of getting your inputs with multiple realizations in a Monte Carlo simulation is sampling. And so sampling is purely, picking a value from the input probability distribution. Okay, and so we say sample, that just means we pick a value from it. And as we'll see in a bit, as we look at a few more models, you see we can either pick that value at the beginning of the realization, and so then we'd have one value for the whole simulation or realization, or we can, select it at different times randomly. Different times we could select a different value, and then in that case we would be representing more of a stochastic process. Okay. But so sampling those values, that's where the probability distributions really come to the fore. The probability distribution provides just sort of a compact representation of the population, and it just then provides an easy way to select a value based on, basically to randomly select a probability and transfer that to a value for the inputs. So in Monte Carlo simulation, what typically happens is the model is run a large number of times. So that's the entire system is simulated a large number of times so that samples are taken from the input population many times. Each simulation is equally likely, and is referred to as a realization. And for each realization, each uncertain parameter is sampled. So usually a single value is selected for each realization from a specified distribution. And we use that as a way to, account for the uncertainty in the input parameter. And if we were sampling the distribution more than once during the simulation, then we would typically be saying, oh, we're representing more of a stochastic process or a random process where we're, changing that random value through the simulation. So the main point with running the Monte Carlo simulation is so you have a whole bunch of realizations, and each realization is likely to have a sort of different input value or a different set of input values. And what that means is you're going to get a range of results. So the whole point with the Monte Carlo simulation is that with uncertainty, there's not a single answer. What you're really trying to get is you're getting a range of possible answers, and the aggregation of those results lets you create an output probability distribution, which then lets you look at the probability of a particular result based on your Monte Carlo simulation. So in a static Monte Carlo simulation, and remember static, there's no time, there's just, simulation, there's just a calculation and you have an end value. So for a static simulation, you'd get a range of results for the simulation. In a dynamic simulation where you're marching through time and you have results for each sort of defined time point, you would get a range of results for each simulation time point. And just to provide, GoldSim based examples of this, you can see on the left, we're showing a distribution result element, and so that would be showing possibly the output from a static simulation. So you have a range of values at the end of the static simulation. On the right-hand side, we have a probabilistic time history plot, and that shows that there's a range of values for each time point. And so the range of values are shown with color, and that color represents, the likelihood of the particular value at a particular time. So moving on, let's look at another GoldSim model. And this one is, again, a very simple model. Okay, the model should be up for everyone now, so we'll talk about this one briefly. It is, again, a static model representing the sum of the throw of two die. Okay, and so just to look at the simulation settings again, you can see the time basis is static, so it's not marching through time. We're just each doing a number of realizations. Again, those are set in the Monte Carlo tab of the simulation settings. So in this case, we're doing 50 realizations. And we have two stochastic elements. This stochastic element here is actually the same as this one. It just has an image inserted to change basically the view of the element. What's inside is exactly the same. So you can see here it's a discrete distribution, equal probabilities for values 1 through 6. So each of these 50 realizations, a value will be sampled from each die. And it's sampled once in the simulation, and those are added together, and that gives you your two dice total. This is a really simple representation. So, this is something you could calculate the probabilities analytically, and that's what's shown here on the right side of this model. And, of course, you have the number of combinations, and the probability is just the number of combinations for each value divided by the total number of combinations. Okay, so let's run this model. And very simple model, so it runs very fast. And you can see here's our output cumulative distribution functions, which the lighter blue, the cayenne line, is the simulated total. So the values that were simulated in each of the 50 realizations aggregated into a distribution. And the darker blue line is the calculated or the underlying analytic solution. You can see 50 realizations, it's fairly close, but you see some divergence for that. And then there's another plot we can look at when looking at Monte Carlo simulations, and that's the multivariate plot. Just to show you an example of that, this provides a scatter plot, and in this case I'm plotting, die 1 versus die 2. And this is just the value, the values for each roll. So we have 50 rolls, and you can see the values there. You can also see those tabular form here, what the value for each die is for each roll. From this chart, you can see there's 36 different combinations. We didn't get all those in the 50 realizations. It's randomly sampled, so you would expect that would be the case. The other thing with the multivariate element is you do get some statistics with this element. You get the correlation matrix and then some sensitivity measures and regression coefficients. And you can also use ranks to do these statistical calculations. Okay, so this model is kind of it's sort of a classic stochastic process model in the sense of we're saying these are, completely random. And this would be an example of process uncertainty. And in this case, it's probably related to the data available. The actual throw of the die, if you had enough information on each throw, density distribution within the die, and how the force that was applied from the thrower, and an exact representation of the shape of the surface it was bouncing across, and a whole bunch of other stuff. I'm sure you could probably, deterministically calculate the output of the throw using F equals MA. But that's a lot of work for something that you could, pretty simply and, represent very well just purely as a stochastic process. Okay. So one thing to keep in mind with Monte Carlo models is, in GoldSim it's pretty easy to determine the number of realizations that you would use. And this plot shown on the screen now just is, bringing to light, as you increase the number of realizations, your sample distribution should get closer to your underlying analytical answer or to the values for the underlying population. Okay, so generally, as a rule of thumb, more realizations is always better. You can see 50 realizations on the left hand versus 5,000 realizations on the right hand. And the two lines are much more coincident on the right hand side. Okay, so we've looked at a variety of Monte Carlo simulations and we've talked about probabilistic inputs and the propagation of uncertainty. Now let's kind of talk about the specific Monte Carlo related options that are available in GoldSim for your simulations. So most of those simulation options, as we've seen, are on the Monte Carlo tab, which is off of the Run menu and Simulation Settings dialog. And here you can see on the right-hand side of the screen, you can see what those main options are. These are the number of realizations, which you can set. You can select that a single realization be used by using the Run the following realization only. And you would often use this if there's a specific realization that's providing an interesting value of some sort, rather than running the whole model. However many realizations, you could just run the one realization to look at those values for the value for that realization for troubleshooting purposes or something like that. You can also select a sampling methodology, and we'll talk about that a little bit more in the next few slides. You can repeat sampling sequences, which we'll talk about a little more as we go forward. You can specify realization weights. The realization weights are kind of an advanced feature, and if you're interested in that one, I would encourage you to look at the GoldSim help dialogues as well as the GoldSim manual. And finally, there's the global Monte Carlo result options, and that would be the result options button. And you can see that on the right side there in the dialog. We'll talk about that a little more as we go through the next slides as well. Okay, so the result options button, that permits the setting of default time history element plot styles for the model. And so this is model-wide, it's global. So if you change this, then it will change all the time history probabilistic plots. And we'll circle back to this when we look at the next model. There's also sampling options. So the default sampling method, which we saw in that screen capture of the Monte Carlo simulation settings dialog, is Latin hypercube sampling. The idea behind this method is it causes the probability distribution, the input probability distribution, to be divided into a number of equally likely strata, kind of conceptually similar to the Latin squares method or experimental setup method. So Latin hypercube has the effect of ensuring that the space of the parameter is uniformly spanned. You could either, if you select this option, which is the default, you can also select to use either random points in the strata or use the midpoints of the strata. And so midpoint of the strata would just mean that the strata is randomly selected and then the midpoint is always used. The random points in the strata would mean that the strata is randomly selected and then the exact point within the strata is randomly selected as well. So the other sort of sampling option would be to uncheck use Latin hypercube sampling. And if this is unchecked, then standard sampling is used. And in this approach, you randomly select the number between 0 and 1, and that's used with the cumulative distribution function, which is provided by the probability distribution, to extract a value from the probability distribution based on that input, essentially probability, or that input number, random number, between 0 and 1, okay? So those are kind of the two sampling methods or methodologies that are available to use in GoldSim, sort of out of the box. And just to kind of provide sort of a not a very good example of the difference between these two, but just something to kind of give you an idea. So on the left-hand side, you can see Latin hypercube sampling, and this is from the 2-die model we just looked at. And on the right-hand side, you can see standard sampling. The left-hand side has 11 open or empty combinations, so combinations that are possible that weren't selected in the 50 realizations. And on the right-hand side, there's 12 open positions. So Latin hypercube did a slightly better job of covering the sample space in this case. In most cases, I would say it won't be the difference between the two sampling methods, Latin hypercube and standard sampling, will probably not be important to you. Just as kind of a rule of thumb, you with a small number of realizations, Latin hypercube might be better because you probably get a better representation or coverage of the input sampling space or input parameter space due to the stratification that's used. With a very large number of realizations, the opposite might actually kind of work out. In that case, you might not get as good of a representation of sort of the very fine details of the structure of the input parameter with Latin hypercube due to the stratification that's used to sort of cover everything well. Okay. If you have more questions about the Latin hypercube sampling method or the standard sampling method, these are both covered in detail in the manual and in the help files, and I encourage you to look at those if you're thinking about, changing one way or another, or interested in, custom setting some parameters here. Okay, so to continue on with the GoldSim sampling options, if you select repeat sampling sequences, if that's checked, and that is actually the default, then a repeatable random number sequence is used. And what that means is we're still selecting things randomly, but you can repeat the selection, the random selection process, so that you could reproduce the simulation. And so that has the effect of, we'll talk about this a little as we go forward to the next slide as well, but if that box is cleared and you're not using repeatable sampling sequences, then the random number is based on the current date and time such that the sequence of values selected, that random sequence, is different every time you run the model. Okay. At the bottom here, you can see how from that 2-die model, always the same, I had the repeat sampling sequences checked, and so you're getting the same, combinations of randomly selected values each time you run the 36 realizations in this case. So the advantages to being able to repeat the sampling sequence are that you could run a selected realization for troubleshooting or analysis and know that it will have the same inputs. So if you run your simulation for 50 realizations, say, and realization 36, there's some sort of error that causes the model to, not complete, it's helpful to be able to run exactly that same sequence so that you could select to run only realization 36 to do troubleshooting on your model. All right. The other big advantage to repeating the sampling sequence is that you could send your model to someone else and they'll run it and they'll get exactly the same results. They're still random, but it's repeated random. And so that way, the other people you're working with can see exactly what you're seeing. All right. And so there's quite a bit of additional detail on how this works in the user's guide, and I definitely encourage you to look at that. All right, so let's move on to one more model, and this is a stochastic precipitation model. It's available from our model library. You can see the path to the model library, which is hosted on our website there, and anybody can go there and download this model if they're interested. All right, so this is just a very simple model again. It's generating a stochastic precipitation record. The one difference with this model from the other models we've looked at is if we go to the simulation settings, we can see that there's some elapsed time in this one. So this model simulates a year, and it simulates 25 realizations. So that means it's going to run the simulation for 1 year 25 times, and each simulation, it will have different values randomly selected from these stochastic elements. In terms of the calculation in the model itself, we have this lookup table, which is providing some underlying data, which is just monthly average precipitation. And so that can be selected by month. And then we have these two stochastic elements, which are basically providing random variation. This particular stochastic element is providing the random daily variation. So you see all the stochastic elements we've seen to this point have been only sampled once, which means sampled at the beginning of the realization. This one is resampled, and here's a trigger dialog showing that every time the day changes, we get a new value from the underlying distribution. This distribution is a gamma distribution in this case, which is a closed form theoretical distribution, which GoldSim provides. And then the other thing about this is it's actually correlated, and it's correlated to itself. And so it's a pretty high degree of correlation. So that means that the value sampled today is going to be fairly similar to the value sampled yesterday in general. Okay, and that's what the correlation is doing. The other stochastic element here is a random monthly factor. Again, this is gamma distribution, same one, but the resampling here is different. It changes every month, okay? And again, there's some autocorrelation, but not nearly as high a degree. The calculation of the precipitation rate then is very simple. It's just this monthly mean value scaled by the monthly variation and the daily variation. Okay? So it's just a pretty simple stochastic precipitation record model, but it provides a very nice illustration of the different ways you can do sampling and to generate just sort of a random time signature in a dynamic Monte Carlo model. So I'm going to run this one quick. Okay, completed. So we look at this output, we can see this is a probability plot, time history probability plot, and you can see the colors are denoting the probability at each time point for the values. Okay. So the one thing to keep in mind here with these time history plots, and this comes back to some of the options. So if you go and look at the properties, there's an options button. This options button is actually exactly the same as the one you get from the Run Simulation Settings Monte Carlo tab. You'll get an options button. So it takes you to the same place essentially. And if you change something here, the important thing to note is that this is a global change. Okay? So here you can see I changed that to green, right? So this is in one of these, but now if I open up the other one, the change is still there. So that's what we mean by it's a global setting. It'll affect all the time history probability plots. The one thing to notice with these time histories is there's probabilities, but there's also these other options you could do. Custom statistics, a single statistic, all realizations or a single realization. And if you do a single realization, then you see the values for that realization. Just one thing to be aware of with this model is this random precipitation representation method isn't actually necessarily a great way to represent precipitation. You probably don't want to use it in your models. You see that you don't have any zero values. That's commonly with simulating precipitation, you want to use some sort of modal form and use maybe like a Markov chain type thing so you can switch between states. So you have dry states and wet states so that you can actually get zero values because it would be highly unusual for it to rain every day, most places. Okay. So that's our stochastic precipitation record model. So let's go back and in the time we have left here, get through the last few slides in the deck. All right, so we just looked at these display options, and again, the point here was these are global options, so that if you change these in either the Monte Carlo tab of the simulation settings or for a particular time history result element, it is a global change. It will show up in all the other plots. One thing which we didn't really
touch on much today looking at the plots is this realization, classification, and screening. This is actually a very powerful tool, but it is an advanced feature. It would be similar to conditional plotting, or it's a form of conditional plotting. It would be similar to like the faceting you can do on R with plots, things like that. But I would encourage you, if you have a whole bunch of realizations in a complex model, it's a very powerful visualization method, and it's actually relatively easy to use. And I think you could just look here in the GoldSim's User's Guide and easily figure out how to implement that in your model. Okay. We also looked a little bit at the other display options that are available, and those are mostly in terms of changing what you plot, whether it's a realization, all realization, specific probability, a specific statistic, which would be like a probability level. All right. So we've been through sort of Monte Carlo simulation in general, Monte Carlo simulation in GoldSim. The big point here is we want to propagate uncertainty from our model inputs to the model results, and see what that means for our model. So to sort of wrap things up here, we'll go over sort of the standard questions we get here at GoldSim related to Monte Carlo simulation. And one of those is the question of how many realizations do I need? And this, the answer, I guess the technical answer to that is, you want to adequately examine your input parameter space. So you want to use a large enough number of realizations that if as you're sampling your input parameter from your probability distribution, that your sample, all those values that were chosen across all the realizations, that the statistical moments or properties of that sample, agree well with the underlying population or input probability distribution. Okay, so that would be like the sort of more technical way to check it. And so that's really what you're looking for, and how many realizations. You want enough realizations that you adequately examine the uncertainty in the input parameters. There is a much simpler way to look at this, and that is just purely to look at plots of the output. And here you can see plots from the precipitation model we just looked at. And you can see on the upper right, you have the time history with 25 realizations. The lower right, you have the time history with 25,000 realizations. And the important point here is that the maximum precipitation rate with 25 realizations is 1 inch per day. And with 25,000, you're up more to 3 inches per day. So if you're concerned with, adequately representing the possible maximum precipitation, you probably need more than 25 realizations, because you're just really not sampling the parameter space well enough. Okay. The other question we frequently get is, why use Monte Carlo simulation? And really, the reason to use Monte Carlo simulation is to deal with uncertainty. And so that's uncertainty related to input values and uncertainty related to physical process representation. It is difficult to completely and accurately represent a real system. And so with that uncertainty, the thing with Monte Carlo simulation is it provides a range of results. Each result is associated with a probability of occurrence. And so you can use that to look at risk. So risk can be defined as the intentional interaction with uncertainty. And risk is a consequence of action taken in spite of uncertainty, right? That's kind of a definition of risk. So therefore, Monte Carlo simulation provides a route, and a very good route, to sort of addressing risk, because you've quantified your uncertainty, and you know what the uncertainty of your outputs are from your output probability distribution. And so, right there you have a way to address any risk that there might be from that system. Okay. And in terms of, why to use Monte Carlo simulation, again, as I said, it's the uncertainty in inputs. And so that would be input uncertainty and process uncertainty. In general, input values are uncertain. Data have a precision range, so it's very rare that you work with more than a couple significant digits probably. And there's also process uncertainty, so it's hard to represent complex physical processes, and generally there'll be some, wiggle room introduced by how you're approximating that process. Okay, so those are really the reasons to look at Monte Carlo simulation, and I think that's probably a good place to wrap up today. So thank you all for coming, and I'll stay online here for a little bit if anybody has questions or wants to discuss anything. We'll be here for a while, well, at least another 5 or 10 minutes. Also, feel free to send us an email, um, support@goldsim.com, if you have any questions as well. All right. So I do see one question coming in there, so give me just a second.